Hey everyone. So, like Joseph said, welcome to our second official meeting. Let's just get started with our first presentation on artificial intelligence.
Sorry to interrupt, but William will be uh recording this meeting, so just wanted to put that out there. Like we do for like most of the meetings, we'll record them and put them on the YouTube page. So William, you can start recording now.
Alright. So before we get into machine learning, we have to actually understand what learning actually is. In the Merriam-Webster dictionary, it is defined as the activity or process of gaining knowledge or skill by studying, practicing, being taught, or experiencing something. Tom Mitchell explained that a computer program is said to learn from experience with respect to some classes of task T and performance measure P, if its performance at tasks in T as measured by P improves with experience E. You can move on to the next slide. So now to get down into what exactly is machine learning. For many problems, it's difficult to program the correct behavior by hand. For example, recognizing people and objects, understanding human speech. There's just a slight problem of how you're able to program that exactly. So the machine learning approach is to program an algorithm to automatically learn from data or from experience. For example, why might you want to use a learning algorithm? We can move on to the next slide again. Hard to code up. So the reasons why you might want to use a learning algorithm, because it's hard to code up a solution by hand, for example, vision or speech. You want the system to need to adapt to a changing environment, for example, spam detection. That's what online chatbots are used for, especially in websites like Twitch. There's loads of chatbots out there that will monitor the chat to make sure that certain words or behavior isn't followed. Want the system to perform better than the human programmers? That's one of the actually ethical questions that's arising today, because the human programmers are worried that the artificial programmers are going to take their jobs. And finally, privacy/fairness. For example, ranking search results. This is what is used by Google to rank the search results. It is what when you search up dog, it's probably more likely that it'll pull up a National Geographic post or a more trusted source than some random Weebly personal custom website that nobody has ever heard of before. Next slide. It's similar to statistics. Both fields try to uncover patterns in data. Both fields draw heavily on calculus, probability, and linear algebra, and share many of the same core algorithms. However, it's still not statistics, because statistics is more concerned with helping scientists and policymakers draw good conclusions, while machine learning is much more concerned with building an autonomous agent. And statistics puts way more emphasis on interpretability and mathematical rigor, while machine learning puts more emphasis on predictive performance, scalability, and autonomy. And that sort of makes sense, because statistics is used in the science lab, while machine learning can be used for a wide array of things, which I just covered in the last slide. Relations to AI. Nowadays, machine learning is often brought up with artificial intelligence, AI. AI does not always imply a learning-based system. For example, symbolic reasoning, rule-based system, and a tree search, etc. are all things part of the learning-based system. Because the learning-based system is learned based on the data, more flexibility, good at solving pattern recognition problems. This is why some AI can distinguish a face of a dog from the face of a human. Relations to human learning. Human learning is very data efficient, an entire multitasking system. I mean, we're able to see, talk, move our hands, etc. But I mean, it takes at least a few years for us to pick up all of those things. For serving specific purposes, machine learning doesn't have to look like human learning in the end. In fact, it borrows ideas from biological systems, for example, our neural networks, and it may perform better or worse than humans. For example, Tesla's auto-driving feature. Tesla claims that it's able that it might be able to self-drive by itself, that's able to identify,
Oh,
uh,
William,
yeah.
I think your audio might be cutting out. So we're just like here, try it again. I think you just usually when that happens, just stop talking for a bit and then start talking again.
All right.
Yeah, sorry to interrupt there.
We're on relations to human learning slide, by the way. Arnav. Yeah. Let me just go over that entire slide again. Human learning is very data efficient. An entire multitasking system with vision, language, motor control, etc. This is all what we do. But of course, it takes a few years for us to pick up all of those tasks. I mean, we don't just, as a 1-year-old baby, we don't just start talking like Abraham Lincoln and start playing tennis. For serving specific purposes, machine learning doesn't have to look like human learning in the end. It may borrow ideas from biological systems, for example, neural networks, and it may perform better or worse than humans. In the case of Tesla, Tesla's neural network is a complicated one because it's supposed to, and sometimes it works, sometimes it doesn't. It's supposed to identify objects on the road, basically make your driving experience easier while also driving safe. However, there have been a few tests where the machine learning algorithm isn't perfect. What is machine learning? Types of machine learning include supervised learning, reinforcement learning, and unsupervised learning. Supervised learning is learning that has labeled examples of the correct behavior. You could think of it as your parents telling you not to put the fork in the electrical outlet, because of course you'll get electrocuted. Reinforcement learning is the learning system or agent that interacts with the world and learns to maximize a scalar reward signal. That, I believe, is a little bit more typical to AI, but you could also think of it applying to kids learning how to actually be in society as they grow up. Unsupervised learning means that there's no labeled examples whatsoever. Instead, you're looking for interesting, quote-unquote, patterns in the data. This is actually a very common machine learning approach, because it just looks for interesting patterns in the data. Because what will happen is that when you give a machine learning bot a few examples, it will find patterns in a certain category. Like, for example, if you show 10 million images of human faces to the AI and 10 million faces of dogs, it will be able to distinguish between the two. It should be able to find a pattern between the two data. A brief history of machine learning. In 1957, the perceptron algorithm was invented, and it was implemented as a circuit. In 1959, Arthur Samuel, one of the leading checkers players of the time, wrote a learning-based checkers program that could defeat him easily. In 1969, Minsky and Pappert's book of perceptrons described limitations of linear models. In the 1980s, there were some foundational ideas that led into wider understanding of machine learning. Connectionist psychologists explored neural models of cognition. In 1984, Leslie Valiant formalized the problem of learning as PAC learning. 1998, backpropagation rediscovered by Geoffrey Hinton and colleagues. In 1988, again, Judea Pearl's book, Probabilistic Reasoning in Intelligent Systems, introduced Bayesian networks. In the 1990s, the AI winter, as it was called, was a time of pessimism and low funding for AI. But looking back, the 90s were also a sort of golden age for ML research. For example, the Markov chain, Monte Carlo, variational inference, kernels and support vector machines, boosting, convolutional networks, reinforcement learning were all sort of breakthroughs in machine learning research. In the 2000s, applied AI fields for vision and NLP and etc. were examples of machine learning being adopted in certain aspects of society. In the 2010s, there was a much deeper learning for the machine learning community. From 2010 to 2012, neural nets smashed previous records in speech-to-text and object recognition, and it was reaching an increasing adoption by the tech industry. In 2016, AlphaGo defeated the human Go champion. And 2018 to present day, machine learning is now generating photorealistic images and videos, like the chatbot we have in our Discord right now. Computer vision. Object detection, semantic segmentation, pose estimation, and almost every other task is done with machine learning. As you can see here in the top left, you can see a few images of blue, yellow, orange, basically colors of the rainbow being associated with each other. Now, some of those are humans, like, dressed up as certain, just coded themselves in that, or it could also be the machine learning identifying new objects. In the bottom left, you can see the machine learning identifying joints just from looking at a picture. In the top right, you can see machine learning being used to make art by just using sample images. You can see the Boston Red Sox hitter, and then at the bottom, you have what looks like a bubblegum packet. You wouldn't even know by looking at the bottom image that you were looking at a Boston Red Sox picture, as you can see in the other four images as well. In the bottom right images, it shows a sample image where there's a question prompted to the machine learning bot. What is there in front of the sofa? Ground truth, table. Table, table, chair. It is able to determine that based off of many other samples that it has been fed. How many leftover donuts is the red bicycle holding? Ground truth, 3. As you can see, the AI actually sort of has a sort of, how do I put this, a little dilemma between choosing from 1 to 3. Because it can see 1, 2, and 3. But because it actually knows how to count, thanks to the data that has been fed into it, it is able to determine that there are 3 leftover donuts that the red bicycle is currently holding. I believe this next slide is going to be presented by Sahil.
Yeah, anyways, back to what William was saying. Some other examples of machine learning is like a speech bot, so like Alexa or Google Home now. But yeah, it's just a speech assistant that can automatically produce a response to any input. It's like the chatbot we have. Right. Another real world example is machine translation, meaning like from any other language, it can be translated to another language. That's how Google Translate works as well, and sentiment analysis, so topic modeling and spam filtering for like messages. All of those are under the guise of machine learning.
Hang on, I actually want to pause you there, Sahil. Another reason Google Translate, because I'm actually a Latin student, I can testify to this. Google Translate has many languages there, but not all of the languages that it has in its database are accurate. Because Latin, in order for Google Translate has the Bible and the Hebrew text as samples for its Latin. It uses the samples from that to try to translate from Latin to English. However, not all of that is correct, as there's different conjugations in Latin that's different. So, just be careful in those. Like, that's just a good example of insufficient data being used. Alright, you can move on.
Yes. Sadly, even with lots of data, machine learning will still make mistakes, and sometimes a human is better for that. So next slide. All right, another example is it playing board games, or actually a video game too, called Dota 2. Next slide. And finally, one of probably the most biggest examples is the recommendation system. So like when you go onto any social media app, whatever you're recommended is almost entirely based on machine learning and like tags. So if you read a book about cooking, for example, then you'll be recommended other books about cooking, and like that. That's how TikTok and YouTube all work. All right, so an ML workflow. To know if you need to use ML for any really given project, there's usually a set of steps you can follow. So first, should I use ML? The main thing. Is there a pattern I can detect? Can I solve it using without using an ML? So like a formula, and do I actually have data? If the answer is yes, then you can continue with the steps. First, you have to gather and organize data because machine learning relies almost entirely on data, and without it, it's kind of just guessing. First, then establish a baseline, and then choose a model for what your machine learning process should be based on. Optimize it in any sort of way. Make a parameter search, and then finally analyze the performance mistakes, and if needed, go back to step 4 or 2, which is choosing a new model and organizing more data. Interpreting machine learning systems. Sometimes you need an algorithm with pencil and paper, and translate that math into code. An example of this is array processing using NumPy. We can vectorize computations, express them in terms of a matrix or a vector, and exploit the efficiency of how fast the math computers can do math. This makes your code much more cleaner and much more readable. The image, yeah. All right. So some of the examples of neural net frameworks you can use is PyTorch, TensorFlow, JX, and other ones. They have automatic differentiation, compiling computational graphs, libraries of algorithms and network primitives, and support for GPUs. And all the above libraries shown are in Python because that's usually the most simplest. Java has Java ML and DL4J, and if you want to use C++, you can use MXNet. That's that. All right, so here are 2 examples of a Java machine learning program and a Python machine learning program. As you can see on the top 2, the top lines, the image on the right is using TensorFlow, which is a Python library, and the one on the left is using it's using MIJTR, JITR.
Yes.
Yeah.
Just to add on to what Sahil said, the main reason this is here is just to emphasize to you guys how much simpler it is to use Python over other languages. So, for example, the TensorFlow screenshot that I included captures basically the entire process of training an ML algorithm. You're defining the model, you're compiling it, you're training it, and you're evaluating it. While if you look at the one that's written in Java, it doesn't even get to defining the model. So the main reason here is just to show you guys how much easier it is to use Python and TensorFlow.
Can you go back? I'll do like one thing that is kind of misleading is like a lot of stuff at the beginning is just templates, like imports, like at least like array list, array random, like those 3 you can actually no, that's dumb. I mean,
All right, moving on.
All right. Preliminaries and nearest neighbor methods. All right, so as an introduction, because this is the first real meeting of machine learning we have, today and for much of this course, we'll be focusing on supervised learning. This means we're given a training set, inputs, and labels. And our goal is to get a desired output. Yeah, our task can be object recognition, image captioning, document classification, speech to text, and our labels will be an image, text, or audio. And our result wants to be in the object category, a caption, a document category, or just text in general. All right.
Okay, so I'll be presenting the next few slides from here. So the next big topic would be input vectors, and this is so essentially when a human sees this picture of a cat, I see that it's like a cat with certain color and a certain background. but computers don't see that. Computers just convert everything to numbers and binary, as y'all probably know. So in the picture, you can see what a computer would see. It's just a bunch of numbers, and the computer's job is to kind of like identify what those numbers mean, and with that data, come up with what it is fully. And one more point I wanted to make was with machine learning, this is all based off of probability and statistics. So, especially in image classification, as shown, the it's saying the computer is saying based on the all the numbers that it received, there's an 82% probability that it's a cat, 15% probability that it's a dog, 2% probability that it's a hat, and 1% that is a mug. So I just want to emphasize that this is all based on probability, and usually they'll just pick if it's 82% cat, they'll say okay, it's a cat, and in this case, that's right. So machine learning algorithms need to handle lots of types of data, such as images, text, audio waveforms, credit card transactions, etc. So, a common strategy for this would be to represent an input as an input vector in RD, and representation would be mapping another to another space so it's easy to manipulate. Vectors are a great representation since we can do this in linear algebra. So, as you can see with the diagram below, it kind of shows images and vectors and how a computer would really read like the different shades of this. So it says can use raw pixels, and then you can do it much better if you complete a vector of meaningful features.
Aren't there
Okay.
AIs that do that, like from a series of pictures? Like they like instead of having like 5,000 pixels, like you can get like 100 sliders that define it.
Sorry, could you repeat that?
Could you repeat that, Madhav?
So, aren't there like already like some models that are trying to take like certain pictures that are maybe like 10,000 pixels, and then like they get like that are like oftentimes a lot similar, like they're all black and white, like pictures of dogs, for instance, and from there like just get like sliders based on those.
Are you by sliders? Are you talking about convolutions and convolutional filters?
Yes.
Okay, yeah, we'll get into that a little later. That's a little more advanced convolutional neural networks. We'll get into those.
Okay. So back to input vectors, I guess. So mathematically, our training set consists of a collection of pairs of an input vector where x is an element of RD and its corresponding target or label t. So if t is a real number, for example, like a stock price, this would be an example of regression, which is I think Arnav pointed out last meeting. It's kind of like a topic you'd learn in statistics if you take that class, but essentially it's like mapping. Let's say if you have like a set of points and then you make a line of best fit so you can predict where values would be. That's the example of regression. Or classification, where t is an element of a discrete set, so it's not a real number, and the set can carry an array of values. So these days, T is often a highly structured object, for example, an image. And just one clarification I wanted to make. So whenever you see like what you guys might see as exponents, these are actually superscripts, and they don't have anything to do with like an exponent in math. It's something completely different. So
So
now
just
Art.
yeah. So just to get our feet wet a little bit with machine learning, I want to introduce the topic of nearest neighbors. It's a very famous algorithm that's used to classify. It's used to make. It's used on classification data. So, for example, if you had to classify between a cat and a dog based on certain features, such as snout length, length of fur, etc., that would be a classification test. So you could use something like k nearest neighbors on that. So, suppose we're given a novel input vector x we'd like to classify, and we have data that helps us represent this novel input vector x. What we can do is we can find the nearest input vector in the data that's closest to x, and copy its label and assign that to our novel input vector x. So this formula might look a little confusing at first, but it's not too complicated. I'm sure most of us are familiar are familiar with the distance between 2 points formula in algebra. So that's basically what this is. It's calculating the distance between 2 points, which we can then minimize to find the closest vector. So yeah, that's what this algorithm is saying. They're trying to find an example x star t star from the stored training set closest to x, where we minimize the distance between our given x and the x in the training set. And then we can copy over t star as our output y. So this is sort of a visualization of what that would look like. We have two separate classes, black dots and red dots, and they have certain features along an x1 axis and an x2 axis. So using k-nearest neighbors, we can tell that if we get a new vector that lies right here, we can pretty confidently classify that as being a red dot because it lies within the decision boundary here. And the same thing, if it lies, let's say, over here, you can pretty accurately classify that as being a black dot because it lies within the black dot region. So that's the same thing here, but now instead of black dots and red dots, it's blue triangles and red circles. So in this case, the data is actually much more separable. So you're able to make what's called a decision boundary. This is usually what you end up with. You very rarely end up with data like this. You're more usually going to end up with data like this. In 3 dimensions. So instead of having a 1D decision boundary, now you're going to have a 2D decision boundary. It's a little hard to wrap your head around, but as long as you can understand the concept of what the decision boundary is. The one thing k-nearest neighbors suffers from is it suffers from what's called noisy samples. Other algorithms don't have too much of a problem with this. So for example, if you get a data point here, it's equally close to this blue square as it is to this red dot. So it's difficult to determine which one you should classify it with. So that's why what we do is we have this hyperparameter called k, which essentially tells us how many neighbors we have to check with. So if we increase the number of neighbors to check with from 1 to, let's say, 5, now this noisy solution problem is solved. Because if you have a data point here, your 5 nearest neighbors 4 of them are red dots and 1 of them is a blue square. So you can accurately say, okay, it's going to be a red dot. It's not going to be a blue square. So yeah, that's what this is. So you increase it from 1 nearest neighbor to 3 nearest neighbors. And now you know, okay, it's not actually a blue dot. It's not actually a blue square. It's a red dot. So here's just another graphical representation of how in keeping the number of neighbors low versus keeping the number of neighbors high. So here it's it suffers much less from what's called overfitting. So in this case, you can tell that there's a lot of blue dots here that are being classified as blue circles here that are being misclassified as yellow circles, versus here you have a lot of yellow circles that are being misclassified as blue circles. So if you select a lower number of neighbors, that problem is usually solved. So you're able to make more accurate decision boundaries with the lower number of neighbors. So choosing a K is what's called hyperparameter tuning. It's a pretty big problem in machine learning, more so for neural networks because there's a lot more parameters you have to choose from. Stuff like learning rate, the number of layers you want in your model, how much dropout you want, what activation to use. There's a lot of stuff you have to decide from. For k-nearest neighbors, the only hyperparameter you really have is what your K value is. So if you have a small K, that's good at capturing fine-grained patterns, but you may overfit. You'd be sensitive to random idiosyncrasies in the training data. But if you have a large K, you could make stable predictions by averaging over lots of examples, but you would fail to capture important regularities. So going back to this image here, even though this is very clearly a blue circle, if you use a large number of K values, it would be classified as being a yellow circle simply because you're averaging it over a large number of neighbors. So the rule of thumb is usually you select K smaller than the square root of the number of samples you have. And another way to decide what K you want to use is through using what's called validation sets. So that's what this is. So K is an example of a hyperparameter. So we tune hyperparameters using validation sets. We have a train set. We select a random K value. In this case, here it's 1, here it's 3, here it's 10. We calculate the error based on this K value. So we find that the lowest error is when you choose a K value of 3. And so we pick that as being our K value to then test.
Okay, so now we'll be explaining another part of machine learning, which would be digit classification. So we looked at image classification and kind of how that works earlier. Now we'll move on to digit classification, and this specific machine learning model has decent performance when there's lots of data. General rule of thumb for all machine learning: the more data and the more clean data given to the model, the better it can um, predict like what it has to classify. So the MNIST digit recognition has handwritten digits, and it's 28 by 28 pixels, and there's 60,000 training samples and 10,000 test samples. And compared to this digit classification model, the nearest neighbor is pretty competitive. So on the right, you can see the test error rates for certain machine learning models when it comes to digit classification. Okay, so going on with digit classification, K and N can perform a lot better with a similarity measure. An example would be shape context for object recognition. In order to achieve invariance to image transformations, they try to wrap one image into another image. So distance measure, average distance between the corresponding points on the wrap measures on the warp images. So that's what Arnav went back to the distance formula in algebra. So this achieved a 0.63% error, 0.63%, 0.63% error on MNIST compared to a 3% error for Euclidean KNN. So as you can see, there's different machine learning models, and based on just probability and how these models perform, the error rates can be different. So competitive with convex at the time, but required careful engineering. And below you can see a couple images of the model, like classifying and changing the image. Okay, so another example would be the 80 million tiny images. This was the first extremely large data set, and it consisted of colored images down to 32 by 32 pixels. So with a large data set, you can find much better semantic matches, and KNN can do some surprising things. And a quick note is this required a carefully chosen similarity metric. So this is the same thing, 80 million tiny images, and this kind of shows you the different like groupings. So grayscale input, and that's the pictures in the first row, and then grayscale 32 by 32 siblings, second row, and then high resolution color siblings, average colorization, and proposed colorization. So those are all the different categories of images that were put into this data set. So some conclusions we can take away from this lesson would be that simple algorithm does not work all the time. So that's why we can write a program so that the computer kind of learns and teaches itself. So that's why that's how machine learning came into play. You can control the complexity by varying the k constant, and this also suffers from the curse of dimensionality. Sorry, just have trouble saying that word. But yeah, those are the main questions.
Yeah, just to add on to that, the cursive dimensionality is something that we'll discuss in the next lesson. And because we have a decent amount of time, I just wanted to quickly demonstrate how you would go about writing a k-nearest neighbor algorithm. So I'm going to go into Google Colab. So what Colab basically is it's a platform by Google which allows you to basically run code in what's called a Jupyter notebook on their machines. So you don't have to install anything. All you need is a Gmail account to sign up. And they give you access to GPUs and TPUs, which are really good for machine learning. GPUs allow you to do for much faster matrix multiplications because they were built for handling graphics processings. And TPUs were specifically built by Google to process what's called tensors, tensors are basically the building blocks for machine learning. We'll learn about those later as well when we actually introduce machine learning libraries. Okay, so our goal for today is we have what's called an iris dataset. It has three classes, the iris versicolor, the iris setosa, and the iris virginica. These are three different flowers, and we are given their petal length, their petal width, and their sepal length and their sepal width. And based off of those four values, we have to classify which class a given data point falls into. So this is very obviously a classification problem. So we're going to utilize k-nearest neighbors for this. If you guys want, you can follow along, and if not, I'm going to share this notebook in the club updates channel after the meeting's over. All right, so we're just going to import some libraries for now. Some basic libraries that are you almost always import these when doing machine learning. sklearn is a library that was built, I think, around a couple decades ago. It mainly contains a lot of the statistical methods like linear regression, k-nearest neighbors, support vector machines. And that's mainly what it's used for. It's really good at those, and it contains a lot of helper methods. So, for example, this one right here. Let me finish typing this out. Train test split allows us to take a training data set and split it in by a certain percentage value. So let's say 20%, that's the value we're going to use. We can split the train data 80% into a train set and 20% into a test set. Matplotlib is a library that allows us to basically plot images, plot graphs. It's very helpful for data visualization if you guys have ever worked with that. Let me just import some more stuff. Okay, and now we import the actual algorithm that we need, which is the k-nearest neighbors algorithm. Okay, hopefully I didn't misspell anything. There's a high chance of that because I don't have autocomplete. There's most likely something that I misspelled. I guess not. Okay, so let's actually load the data set. There's a very handy function from sklearn. They have a datasets method that allows you to load a bunch of data sets. So all of these, so load Boston, load diabetes, etc. Load iris is what we actually want because it's the iris data set. And we can split this into our X and Y, where Y represents the class label and X represents the data that we have. So iris.data gives us the data and iris.target gives us the label. So I can run this, and then we have our X and Y. If we print out our X, you'll see a huge list of data that we have. Each element within this list is four elements long. So that refers to the petal length, the petal width. Actually, no, I think it's sepal length, sepal width, petal length, petal width. So those are the 4 data values that we are given. And then the Y just shows us what the class is. So the first couple are all versicolor, the second couple are all setosa, and the third are all. So 0 refers to versicolor, 1 refers to setosa, and 2 refers to virginica. And now let's actually use this train test split function to get our X train, our X test, our Y train, and our Y test. So we will use this to actually evaluate our model to see how well it performs. We'll split them based 20%. I think is a good estimate, is a good number. So 80% of the data goes into our train data, and 20% of our data goes into our test data. And this random state is just here simply to make sure that the data is all shuffled around. Okay. So now, really quickly, let's just see what this data looks like. So what I'm going to do here is I'm going to plot a scatter plot with our petal length, which is the second element. So if I print my X here, what I'm trying to do is I'm trying to grab this element and this element and plot them. So this is going to be the X, and this is going to be our Y. It's just some parameters that the method requires. That's what this looks like. Let me zoom in a bit so you guys can see it. So here's what it looks like. Oh my God. Okay. So this is one class. The purple blackish looking dots is one class. The blue dots is another class, and the yellow dots is our third class. So it would be pretty easy to classify these 2 classes, but the difficulty arises around here, where you can see there's a bit of a grouping here. Some of the blue dots go into a place where you think yellow dots would occur. So that's slightly difficult, and because of that, it's possible to have a little bit lower accuracy than you would want. And finally, let me just define our k-nearest neighbors model. It needs a number of neighbors parameter when you're initializing it. So usually you, going by the rule of thumb, it's square root of the number of samples that we have. But usually for the iris dataset, the recommended is about 3 to 5. I'm just going to go with 3. So we fit the model on our X train and our Y train. And then finally, we score the model to see what its accuracy is. And it's 100%, which is actually really good. You very rarely actually see this in machine learning, so it's pretty good to see it. But just as a demonstration, if you increase this number to something ridiculously large, you'll see that, okay, so it requires you to have a less than or equal to number of samples. So something ridiculously large like that, you can see the accuracy is no longer good because if it's 120 neighbors, you're averaging it with every single sample out here. So it's really difficult to actually get what the actual value is. So that's why you usually prefer to keep a low number of neighbors, usually 3 to 5, and that gets you good accuracy. So 3 gets us 100%. So 3 is right now the best. So yeah, that's basically a very simple problem that we solve using k-nearest neighbors. And yeah, that's basically it.
Do you want your so quick question about this?
Hmm.
Does K scale with noise? So if you have more random noise, do you want K to generally be higher?
Well, that depends, right? Because having a value all the way up here also counts as random noise. So if you have it all the way up here, it doesn't really matter. But if it's something like, let's say we have a purple dot all the way in the middle over here, then having a lower number of neighbors would help you classify it more accurately. Does that make sense?
Mm-hmm.
So
Wait,
yeah, yeah.
wait, a lower number or a higher number? So like, let's say if it isn't one, let's say they're like for some reason four, but like those are just like some weird like lab grown variants. Then you'd want the K value to be higher so you can just toss those out.
Yeah, in that case, you want it higher, but if it's an actual meaningful data point, then you'd want it lower. So actually, yeah, you're right. You would want it higher, so that way you could actually make a boundary here and ignore that. But if it's, let's like, for example, if it's an actual meaningful data set, so let's say in one region, there's something weird about, let's say, the weather that causes the plants to grow extremely large, that still counts as it still counts as a class, and you don't want to just label it off as noisy data. So in that case, you would stick to a lower number of neighbors. Does that make sense?
Yeah.
All right. Does anyone else have any other questions? All right. I guess we're all good then. So yeah, thank you guys for attending this meeting. We hope to see you all next week. All right. Have a good one, guys.
All right, see you guys.